Hello everyone. Today we will be discussing the columns tributary area or influence area method, how to do it using AutoCAD and Excel, and how to check the columns using this method. But before we do so, it's important first to talk about the tributary area method. What is it? Why do we use it? And how do we do it? So the columns tributary area method or influence area method is a simplified approximate engineering method. Okay, so we should notice that it's a simplified approximate method and not an exact method. So we cannot build on results of this method. It is used to estimate the load carried by structural elements like columns, walls, or beams. It's also used for beams, not only for columns. So the idea of it is simple. As we can see in this picture here, this is the load path in buildings and structures. It goes from slabs to beams to columns and then to foundation. But what portion of the load is carried by each column? So if I have a grid of columns, what portion of the load will be going to each column? So we can think of it like if the floor load, for example, was rain falling uniformly. Each column collects the rain that falls on the area around it. Okay. So why do we need this method? Again, this method is an approximate method. Using this method, we can estimate columns and walls forces quickly. Like for example, we are on site. We want to give a very quick answer if this columns work or not, a very quick check. We can do it manually, approximately, just to take an idea of the forces inside this column or wall. We can also use it for the preliminary sizing of vertical elements. When the architectural plans are received, sometimes we need to use approximate method to do fast calculations that just to check whether these columns will be used or not, even before we build a model. Okay, so we might use this method in order to quickly size the vertical elements just for schematic design. We also can use this method to check software results and check if model is behaving properly. Any person can build a model, any person can do a model, but garbage in is garbage out. Okay, so if you put wrong inputs, you get wrong outputs. If the model is working properly, it does not mean that the model is correct. Okay, so this could be a quick check we do for like two, three columns and two, three walls, just to get the forces manually in the columns and walls, and then we check the axial force and the results from the software to know if the software is behaving properly or not. Of course, we won't get the exact same result because the model takes a lot of different things into consideration, but at least we get like close results. Also, we can use it when drawings are incomplete and in concept design meetings when we are doing like fast decisions. Before proceeding, there are some important notes you need to remember. This method is only geometric and approximate, okay? It does not give any exact results. Also, it takes into account only gravity loads. So it's not exact because the software takes also into account the seismic loads, the wind loads. So there are a lot of other factors that are taken into account. And the real load in a structure also depends on stiffness, beams, slab behavior, wall scores, irregular grids, whatsoever. So this method does not take any of the following into consideration. And it's just a first estimate, just to approximate the size, for example. But if we like want definite results, we should use a finite element model. So how is this done? Now the concept is clear. If we have a grid of columns, first let's talk about the restraints. In order to be able to use this method, the the plan should be regular and not with a lot of irregularities, and we should be able to define clear polylines for the columns. Okay, so if we have a grid of columns, the influence area is marked by the centers lines between columns. Now we will discuss them more over AutoCAD, but this is just a quick overview. So as you can see, this is the tributary area, which is the mid distance between the columns from each side. Then we define this area by polylines, and finally we can do our approximations. Okay, so now to move to this plan. Okay, so how do we get from here to here? The first thing we have to do is check, is our plan regular? Can we clearly define center lines? Yes, we can. So what we can do now, we can either name the columns first or keep them for last. You need the naming because, like, when you do later on calculations in Excel, you need to know what column you're referring to. And the dimensions are for the Excel later on, we will be checking them. So to begin with the method, this method can be either done by from face to face of an element or from center to center of the element. Now, preferably it should be done from center to center, but again, since it's an approximate method, it shouldn't vary that much. Okay, so we will be having layers for slabs, columns, core walls, openings, whatever. Okay, we choose any layer we want to draw in, but it should be like with a different color so that it should be clear. And then we do the center line between these two, and then the center line between these two. Okay, so we have the midpoint here and the midpoint here. Okay, so now we have defined the tributary area of this column. Okay, so what we do is we draw a polyline here or a rectangle. And then we can remove unwanted lines just to make things clear. So this is the tributary area of the first column. Maybe we can mark it in a different color or something just for it to be clear. So let's say this is in green. Okay, and when we start from one column, it automatically all columns are determined. Like for example, if we take an this internal core, okay, so we have this part here, okay, from this side, and then we have this line from this side. So here we won't be taking this column into consideration because, like, theoretically speaking, we should do it, but in a more engineering sense, this column is carrying almost nothing because, like, there's the opening and there's the core around it, and then we have effectively this space between the columns and the core. So we will be taking into consideration these columns, not this column, in order to determine the tributary area for this core. And then we have it from this side. Okay, so what we can do is draw a polyline from the midpoint of this part to the midpoint of this part. We can first determine them by lines just so that everything would be clear. Okay, so we can draw a rectangle from this side to this side. Okay, so now we have determined the tributary area of this core. Okay, so maybe we can mark it in another color. Okay. Now, since we have the slabs in light blue, let's consider another color. So if you can see here, the the top boundary of these columns have been clearly defined. The right boundaries of these columns have been clearly defined. The bottom boundaries of these columns have been clearly defined, as well as the left boundaries of this column. Okay, so like here, all we have to do for this column is to take into consideration this part and this part. Okay, so we will have, this is the midpoint and this is the midpoint. So now the tributary area of this column is clearly determined. Okay, we can do the same for these columns. Okay, so here we will take this column into consideration and this column. Okay, so this is the first part, which is also clearly determined here, and this is the second part. Okay, so now we have the tributary area for this column. The same is done here. Now we have it defined from two different sides. We still only have this side. Okay, so here we have two options. Either we use this area, we do it like this, and we keep this difference. Or since it's an approximate method, we can, to avoid corners and irregularities, we can do this. It's up to you because it's a pure approximate method. So like if we leave this corner like this, it won't affect anything, but just like for the overall visibility of the areas. Okay, so as we can see, the area for this column is now clearly defined. So we just do this. Okay. Now, if you can see here, we have some irregularities. Let's talk about them. Okay, what we can do here is we have this part. And here, since we have a long wall, we won't take it to its center. We can take it to the face because walls usually carry loads more than columns. So we have this part. Okay. Okay, so the area is determined, the boundary of the area is determined from this side. We still need to determine it from this side, which is here. Okay, so now talking about this area, we won't be taking the distance from this column to this column because effectively the column is resisting a larger area, is carrying a larger force due to a larger area. So we'll be taking the distance from this column to this column. Okay, so now we have this area clearly defined, which is this one. Okay, so moving forward for this column, we have the area. Now we can take into consideration this column and then this column. And from the left side, we already have the boundary. And this will be our area for this part. Okay, now taking this column into consideration, let's do this before. So we have the boundary from this side, the boundary here, and we have the wall from here. And here is the boundary, so okay, so as we said, like here for this corner, we can do the same. We can either like adjust this corner to make them a straight line, or we can just keep it as it is, because we will later on be performing the calculations. Okay, so this is my area. And now the area of this wall is also clearly defined. So we can consider it as from this point to this point to this point, and then to this point. Okay, here we made a mistake because this is not the edge of the slab, this is the edge of the slab. So this part is also carried by this column. This slab's edge is the difference in thickness, because this slab is 250 millimeters and this slab is 300 millimeters. So we will later see why is this useful when we start with the Excel part. Okay. So here let's talk quickly about this. Here I have a clearly defined boundary here, which is this one. So I have this area for this column and this area for this column. And also here I have a defined boundary between these two columns. This will be the area for my column. Okay, so now here, what do I do? Do I take the distance from here to here? Of course, I don't take the distance from here to here because effectively the column is not carrying this whole distance. So what we can do is, okay, we can estimate this area for this column, which is this one for this column. And then we have this area for this column. Okay, so effectively this area will be carrying this part. This column will be carrying the part from this area. Okay, so here we have the distance from here to here. So we will be, we have and the distance from here to here. So it will be like something like this. And then effectively this column will take this area. Here we have leftovers in this area here. Okay, so here this is the area for this column, and this is the area for this column. Okay, and so on. We can continue this way. Here the boundaries are clear too. Okay, so when we finish all of this, we will arrive at these shapes. Okay, so if you can see, what I did for each line is that I increased the line weight of it in order to be able to see it clearly. And I changed the colors for them. And also what I did is that I hatched my areas for them to be more visible. Let's see. Okay, and with the same color for each part. Let's see, this is in yellow and whatsoever. I also increased the line weight for each part. Okay, and this one too. And I did this for all areas. Okay, So what I arrived at finally is this shape. Okay, so like as we can see here, this shape is similar to this shape is similar to this shape. The one we agreed here is this one. And everything else. Okay, so now after having clearly defined areas for each column and wall, what I can do next is that I can name my columns C1, C2, C3, my walls W1, W2, W3, and this is my core wall. Okay, an important thing to consider when calculating the area is that the area of the openings should be removed from it. Okay, so effectively this should be my area. Okay, I should remove the openings from the area because we have no slab in place. So after naming my columns and walls and then determining the dimension, I can move to the Excel part. Okay, so this is an Excel that you can prepare by yourself. It's just like a manual calculation, but instead of doing it for each column, you can just replace it in Excel. So the parameters needed are columns dimensions, the tributary area determined by AutoCAD, slab thickness, loads, and materials. And then these acting loads are required. And what will be calculated are the service and ultimate loads by the load combinations, the capacity, and then the check whether this column is safe or not. Okay, what's meant by safe or unsafe is that under gravity loads, is this column capacity less than or greater than the ultimate load imposed on this column. Okay, so here as we can see for the column dimensions B, H, and L, if we go to the general parameters, we have this is B, this is H, and this is L. And then for the tributary area, we have A and B, which are A in the X direction and B in the Y direction. And then for the thickness of the slab, the thickness of the top slab is considered. So that's why I told you we need to name the columns and then check their dimensions. Okay, because this whole part is only for one column in plan. Okay, depending on the number of floors. I may have like one floor, two floor, three floors. You can adjust the Excel based on the number of floors you have. Okay, so if we go back here, we talked about inputting the columns dimensions, then the structure, the data, tributary area, and the input loads. Okay, in order, after inputting the dead and live loads, superimposed dead loads and live loads imposed on the slab, we need to, the Excel actually calculates the service and ultimate loads. The service load is just the dead load plus the live load, while the ultimate load, since we are only considering gravity combination, we are using only this combination without this part, which is 1.2 dead plus 1.6 live. Okay, because as we said, it's an approximate approach. And then the capacity of column is calculated as follows: as 0.85 F prime C, area of column minus area of steel plus area of steel. Okay, here for the area of steel, what could be done if we don't have a definition for the steel is that we can take it as 1% of the area of concrete. So area of steel or raw steel is 1% area of concrete. Okay. Okay, so here let's assume that this is column 1. Okay, this is C1. Okay, so the dimensions are 0.2 by 0.6. Okay, for now we will assume that these are the dimensions of the column in the whole building and that it's a nine floor building plus roof. Okay, and with a floor height of 3 meters. Now, of course, for the basement, it sometimes varies. Let's say for the ground floor, this is 3.5. Maybe for upper floors, let's try if this is 2.8. This is 2.8, just as an example. Okay. So the area we have two options to input the area. Okay, we either input uh, width by depth, which is A by B, and then this area is calculated using A times B, or since sometimes we might have irregular areas like this part, so what we can do is that in AutoCAD we write area, we select object, and then we select this part, okay? So the area here is 27397 to 70.8, but this is in millimeter squared, because this is the area, this is the parameter, but in millimeter squared. So what we can do is that we can convert it into meter squared and then input it here. Okay, as for the thickness of the slab, it depends on the like maybe we can start from a preliminary thickness because when we will be doing these calculations, we won't be having exact slab thicknesses. So we can start from a preliminary one, consider 0.2 or 0.25 based on code calculations. The dead load imposed is also can be approximately estimated as 0.4, 0.5, 0.6, or the calculations at this point should have been done because maybe we already did the model, but we need to check the results of the axial force in this model and if the model is working properly. So we will already be having our dead loads and live loads. Okay, so what the Excel does is that it first calculates the dead load by the combination of own weight of the slab plus own weight of the column plus the superimposed dead. So the own weight of the slab is this part, which is concrete density 2.5 ton per meter cube times the thickness and then times the area. And then, okay, this is one, is times the thickness times the area. And then the column on weight is the B times H times L times 2.5. And then adding the SDL times the tributary area. So here, the aim is to find the load in tons. Okay, so if I have the SDL in ton per meter squared, I have to multiply it by the area to get it in tons. And if I have the density as 2.5 ton per meter cube, I should multiply it by 3 dimensions in order to get it per ton. This is as for the dead load. As for the live load, it's just the live load imposed times the tributary area for the column. And then the service load is dead load plus live load, and the ultimate load is 1.2 dead load plus 1.6 live load based on ACI combination. So this is the part that is important, okay? The cumulative part, okay? So when I have, let's say, I have this column, this is the foundation, first floor, second floor, third floor, whatever, this is the roof, okay? So I have loads on all parts of the buildings. I have these loads and these loads, these loads. Okay. So from each floor, the column will take the loads. Okay. So on the roof floor, the column will take loads based on this part only. Okay. This column will take loads based on this part plus what is being transferred from this part. Okay, so the load here is cumulative from the top of the building. So the axial diagram of the column should be something like this. Okay, so as we go down, the load increase because each part of the column is carrying the uniform load from the slab above it plus what the column above it is carrying, which is cumulative from the roof going down. Okay, so at each floor, the axial load in the column will increase, reaching a maximum on the base. This is what should be seen in the model. If this is not the behavior, so there should be something wrong. In the second part of this video, we will do a comparison between this method and the model in order to like do it, like see in firms how is this uh, method used. Okay, so after accumulating these loads, okay, we have like on the foundation the load is applied load cumulative is 750 tons. However, the capacity is 282, so this is unsafe. The capacity is, as we mentioned in this part, this is how the capacity is calculated from the ACI code. And then it's compared to the P ultimate. This should be greater than this part, okay? If it's greater than the column is safe to carry gravitational load. If not, then we need to increase the section. Okay, so here maybe we can do like a bit trials. Let's say that on the fifth floor, this should be 0.3 by 0.6, or maybe we can keep this 0.2 but do this 0.7, for example. Okay, but if we increase the dimensions of a column here, the ones underneath cannot be smaller than it. So all of this should now become 0.7. Okay, we can start with, now if the column is like this, we can do like a larger column and then a smaller one. Okay, the bottom column should always be larger or equal to the column above it. So then I need to try for this part, maybe here I increase this a bit. It works, so I have all of these. Okay, maybe here I can start increasing the width instead of the length of the column. Okay, so here it works until here, but here I need even a larger column. So let's say this is 1 meter. Okay, I only have a problem with these two. So let's say this is 0.4 by 0.4 now. This is a preliminary sizing of my column. Okay, starting from the foundation, uh, I have these two columns the same, then these three floors the same, then these floors, then this floor is different, and then maybe I can make this floor 0.8 so that for the easier of construction, for example. So maybe I can start from these sections of the column and then using the model, I can check whether I need larger sections because I have other consideration like wind and earthquake, and or I can use smaller sections because like the tributary area was effectively smaller than the one calculated in AutoCAD. Okay, so this was everything concerning how to calculate the tributary area. What we will be doing in the second part is that we will be comparing the results for some columns for a real project uh, by manual calculation and software results, and we will be knowing like how is this method effectively used.